So we finished last time with an example where we calculated the pH of a weak base solution. We took and determined the concentration of hydroxide using the Kb. The question about YouTube. I haven't uploaded things onto YouTube. That's going to be this weekend. I did not have enough time to do that with working on your guys' quiz and the like. Okay, so hopefully this weekend I'll be able to, hopefully tomorrow I'll be able to upload stuff onto YouTube. That would be my ultimate goal. And when I do, I will let you know. Okay. So we did our calculation of the pH by calculating our hydroxide ion concentration first, in the same way that we ran the calculation and did a calculation for the weak acid. And we had to check our assumptions, and when we checked our assumptions, things worked out. And so, and we did a little bit more on the checking of those assumptions as after we finished the lecture last time too. So what we're going to do now, we're going to move on to our next section, which is about polyprotic acids. Okay, so polyprotic acids, right, are acids that have more than one ionizable proton for them. So our example, I'm just going to use this one example. I think calculations of pHs with polyprotic acids, and in particular concentrations of pHs and the concentrations of the ions and that kind of thing, it's a little bit beyond the scope of what we really have time to do in here in 102, but we do need to know some key things about this. So our example is going to be, you can see here, phosphoric acid. It's a triprotic acid, right? So a triprotic...
I have a question.
Yeah.
Is that supposed to be hydroxide at the end?
No, it should be water. That looks like a typo.
Is it hydronium or water?
No, it's hydronium. You're right.
Okay.
Sorry, it's a cut and paste error. Come on. So give me a second. Thank you for pointing that out. First time use of these slides. So give me a moment and I will correct that. Oh, sorry, H3O plus. I just said it. Ooh, come on. 3. Plus. There we go. Okay, so give me a second. I'll cut and paste that and make sure that's all proper in there. That's better. Thank you. Okay, I was talking about bases, and I must have cut and pasted the base equation in there. Let's blow that back up. Let's see. Here we go. Ah, better. Thanks, Nora. Okay. So, where were we? Okay, we have our polyprotic acid where we have the first proton of phosphoric acid reacts with water to form hydronium and dihydrogen phosphate. And so we get a Ka expression, as you can see here, right, where in the numerator we've got our dihydrogen phosphate and our hydroxide, and in the denominator we've got our H3PO4. So what we're going to see, we're actually going to look at this a little bit more when we talk about buffers, because I think it's easier to deal with these in buffers, because what's nice about a polyprotic acid is that there isn't just one Ka, right? There are 3 of them. So the second Ka takes that dihydrogen phosphate and it reacts with water to form hydrogen phosphate or biphosphate and hydronium. And of course I have to go and edit those too. So give me a second. I'm going to go edit what we just changed the one thing. I'm going to keep those. I should just edit this right now and get everybody on the same page. This should be hydroniums up here. Ah, can't fool me. That's better. Okay, let's go back into that. Okay, so we make that hydronium from the reaction of the dihydrogen phosphate and water, but in each of these particular equilibria, the first one obviously is starting here with the phosphoric acid. The second one starting with dihydrogen phosphate. So there are a couple ways that you can get from phosphoric acid to dihydrogen phosphate. One of them is you can titrate that first proton. You can add sodium hydroxide until you get rid of that first proton. And then you're left with a bunch of dihydrogen phosphate remaining. Another way you can get that dihydrogen phosphate into solution is to say, start with something like, right, maybe a sodium dihydrogen phosphate or potassium dihydrogen phosphate. Right, and since that's an ionic compound, right, that ionic compound dissociates to give you the dihydrogen phosphate itself. And we'll talk more about the sodium ions in just a minute. But what's nice is you have these three equilibria, right? Because the hydrogen phosphate would then react to form phosphate and hydronium again, assuming you started with that. Now, all of three of these equilibria are taking place at any given time in a solution of phosphoric acid or dihydrogen phosphate or hydrogen phosphate or just all phosphate. But the main component is going to be whatever you really start with. So if you start with phosphoric acid, since it's a weak acid, it's mostly going to stay as phosphoric acid. If you start with dihydrogen phosphate, since it's a weak acid, but it's also a weak base, most of it is going to stay as dihydrogen phosphate. Or if you start with hydrogen phosphate, it's going to mostly stay as hydrogen phosphate, but it is also it is the conjugate base of dihydrogen phosphate. So what I'm getting at here is a solution of any of these components, any of these acids or their conjugate bases is going to be a somewhat complex mixture. And so that's why we're going to kind of avoid really doing any major calculations with these. But the key take-homes are you have these three Kas. Okay, the Ka1 is for the first proton that gets removed, Ka2 is for the second proton, Ka3 is for the third proton that gets removed. And the Kas themselves, the first proton that gets removed is going to have a larger Ka than the second one, right? Which will be larger than the third one. So each subsequent proton that gets removed is going to have be a little bit less acidic than the previous one. And we kind of know that already, or we should know that already from the stuff we talked about in 14.2 and 14.9 doing the structure work, right? This was the formal charge argument. Essentially what you're looking at when it comes to the formal charges is a comparison of two things, right? You're looking at the comparison of the ions here and here and saying, well, in order to compare the acidity of the acid, you should look at those two ions and say, well, how attractive are those two ions to each other? The more attractive they are to each other, the weaker the acid. And so if we go to our next one, we say, well, how strong of an acid is dihydrogen phosphate as compared to phosphate? What we're really comparing is the hydrogen phosphate attracted to the hydronium as compared to the dihydrogen phosphate attracted to hydronium. And since this in particular has a -2 charge, right, that hydrogen phosphate is going to be more strongly attracted to a hydronium, making the dihydrogen phosphate a weaker acid than the hydrogen or than the phosphoric acid. Okay, and so those subsequent pKa's, not only are they subsequently, as you lose protons, getting smaller and smaller, but having 3 Ka's is actually nice because of something we'll see in the next chapter as we get into buffers. Having 3 different protons that you can utilize with buffers is a very useful thing for creating solutions. Okay, and that's really all we're going to get into with polyprotic acids. You need to be able to identify what a polyprotic acid is and the relationship between the 3 Ka values. So the next thing to look at, and really sort of as we bring this chapter to a close, is properties of salts. So when we talk about salts, remember a salt is just an ionic substance, right? In the ionic substances that we're looking at, it's going to, they're going to have acidity or basicity that depends upon the nature of both the cation and the anion. We have to think about both of those components. And so if we think about the cations being present in a solution, one of the things that we're looking at is the ion that's dissolved. So if we look at a cation of a strong base, we say a cation of a strong base, right? We're talking sodium, potassium, etc., right? Think about a strong base, right? Sodium hydroxide, right? So there's our cation of the strong base would be sodium. Now, when that's dissolved in water, it dissociates, right? We know it dissociates into, right, sodium ion and hydroxide ion. And the sodium ion itself really doesn't have any kind of an impact, any appreciable impact on the acidity of that solution. Essentially, all it does is sits there and it is solvated by the water molecules that dissolve it, that cause it to dissociate. Okay, and so it doesn't have the effect on the acidity. What has the effect on the acidity or basicity of the solution is the other thing. It's that hydroxide, right? So when we think about the ion, the sodium or the potassium ion, those ions will have no effect on the concentration of the hydronium ion, right? If we think about the anion of a strong acid, right? So think HCl, right? The anion of that strong acid, well, the H plus, right, which we know, right, I'm just doing shorthand right now, but we know that's hydronium, right? H plus Cl minus, right? Well, the Cl minus really doesn't do anything but sit there and be solvated by the water. It doesn't have any effect. It doesn't grab onto a proton from water because it's a very, very, very weak base. It's so weak as to be considered negligibly strong, right? And since it's a negligible base, we think about it as being a neutral ion, okay? So salts that consist of cations of strong bases like sodium or potassium, or anions of strong acids like chloride, bromide, iodide, right? Perchlorate. In this case, we're going to limit ourselves to monoprotic acids because hydrogen sulfate's a little different. But in those cases, those are all what we consider neutral ions, right? Neutral cations, right? And neutral anions. And so that's the important thing right there. Ooh, that didn't work. Hold on. And so I want to highlight that for us right here, right? We're talking neutral cations and neutral anions. And those are the, if you will, the conjugate acids and conjugate bases of strong bases and strong acids respectively, okay? Those are neutral ions. For salts that, so if we have a salt that has a cation with neutral properties. So when we talk about, in this case, a cation with neutral properties, we're talking about something like we just talked about, right? With sodium, for example. Oop. Do that again. So sodium, for example, try this again. So we have a cation of a strong base and the anion, which is the conjugate base of a weak acid. So something like sodium fluoride, right? So the sodium fluoride, right, will dissociate, we know, into sodium ion and fluoride ion, right? And so we know the sodium ion itself doesn't have any acidity to it, but the fluoride ion does have some measure of basicity. It does have an attraction to a proton. And so what we would have to take into account now is the basicity of that fluoride, right? And how it reacts with water. Now, fluoride is the conjugate base of a weak acid, which means that fluoride itself is a weak base, right? So it's going to react with water to deprotonate water and form HF, plus hydroxide. Okay. And so now we can think about the fluoride as being a base in and of itself. It's a weak base. The sodium is a negligible acid. And so together they would form a solution that would be basic. You essentially you're putting a base into that solution. When you add that sodium fluoride, you're essentially just adding, of the things that would affect the pH, you're just adding the fluoride. Okay. When it comes to salts in which you have an anion that comes from a strong acid, right? So the conjugate base of a strong acid, something like chloride, you can imagine having ammonium chloride, right? That right there has two parts to it, right? You've got the ammonium part and you have the chloride part, right? And so in that, the ammonium is acidic and the chloride is neutral. And so in a solution with something like a protonated version of one of the nitrogenous bases, that will be acidic. And so you'll wind up with an acidic solution if you have a salt containing one of those conjugate acids of one of the nitrogenous bases and an anion that is coming from, which is the conjugate base of a strong acid, okay? So those are just sort of qualitative versions or qualitative ways to identify, oh, you know what? And I think I didn't start recording. So I apologize, there's gonna be a gap in the recording here. Come on. Oh no, I lied, I did start recording. So that will be on the recording. All right, so this is a really qualitative version of looking at the properties, acid-base properties of these salt solutions, being able to identify, is it going to be acidic? Is it going to be basic? If you want to really compare, you can always compare the cation and anion, and you'll find that if you have a anion that is a weak base and a cation that's a weak acid, you can determine whether the solution is going to be acidic versus basic by comparing the Ka and the Kb of those two ions, right? If the Kb is bigger than the Ka for the base and the acid respectively, right, then it's going to be a basic solution. If the Ka is bigger than the Kb for the acid and the base, then it'll be an acidic solution. Okay. All right. Okay. So when we look at the relationships between Ka and Kb now, let's just take and look at a weak acid and its conjugate base. So in this case, we're looking at acetic acid, right, and acetate, right, where we can get acetate from something like sodium acetate or potassium acetate, some sort of an ionic salt that'll just give us acetate that has the effect on the pH. Now, when we look at the Ka expression that you see here, notice that we've got, right, hydronium in the numerator, right there, and acetate in the numerator and acetic acid in the denominator, right here, right? Oop, what just happened? Come on. Okay, and so that is related to the Kb, because in the Kb you can see, well, okay, yeah, you have hydroxide in the numerator, but you also now have acetic acid in the numerator, right? And you have acetate in the denominator. And so if you were to take and multiply Ka times Kb, right, which you see here, so Ka has acetate in the numerator and Kb has acetate in the denominator. So those would cancel out if you multiply them. And then Ka has acetic acid in the denominator, whereas Kb has acetic acid in the numerator. And so those would cancel out. And you're left with this expression that says, oh, well, that Ka times Kb will equal the hydronium times the hydroxide ion concentration. Oh, that's convenient. That's Kw. And so we have this relationship now. Oop. Hold on a second. Sorry about that. I unshared. Get back to that. The stylus. I've got the new stylus coming at some point. I can't wait. move this out of the way. There we go. There we go. So here we now can say, oh, well, when you have the Ka times the Kb, right, that gives you Kw. And so you get a relationship where you can calculate the equilibrium constant associated with the conjugate base if you know the equilibrium constant for the weak acid, okay? And so the other relationship that we can get out of this, and I'll sort of draw this right up here, is that if you have the pKa plus the pKb, that's going to equal pKw, okay? And so those are going to be relationships that we're going to utilize semi-frequently as well, especially as we get into the next chapter and we start dealing with buffers, okay? But this shows the relationship, and there is a direct relationship between the, the Ka for a weak acid and the Kb for that weak base, right? So it's useful for us to have that understanding. So if we do have a deprotonated version of one, we know how good of a base it is if we know how good the acid, the protonated version of the acid was, right? So to do this, we can use this in a simple calculation of the pH of a weak base solution. You can see where this weak base is coming from the solution of sodium fluoride, okay? So sodium fluoride, we know, if it's dissolved in water, it dissociates and pretty much dissociates completely. So it's going to give us sodium ion plus fluoride ion, right? And the fluoride ion is what we're really interested in. But we're interested in, with the fluoride ion, it's a base, so we need to see how that base reacts with water. So what's really necessary for us is we want to know the Kb. And so the Kb is as simple as calculating it this way by dissolving 1 times 10 to the minus 14 divided by Ka. So 7.2 times 10 to the minus 4, right? And so you can calculate that Kb very, very simply, and you wind up with a value of 1.389 times 10, it's a 9, times 10 to the minus 11 with, in this case, 2 sig figs, so 1.4 if you were to round it here. So we have sort of a setup for putting this together in an ice box. So we can now calculate based on the Kb and the concentration of fluoride, right? We know the concentration of fluoride because our sodium fluoride dissociates completely. And so we can say, well, what happens in this reaction? Fluoride reacts with water to produce hydrogen fluoride and hydroxide. Okay, so there's our chemical equation for that. We have our ice box, which we can start to fill in now. Right, our initial concentration of the fluoride is the same as the initial concentration of the sodium fluoride because it dissociates completely. So we get 0.100, right? These are all in molar. The initial concentration of HF is 0 because it's before the reaction occurs. And we're going to make the assumption here, right, that the concentration of hydroxide from water is 0 as well. So that one says the concentration of hydroxide from water is going to be much less than the concentration of hydroxide from the fluoride ion. And so as the fluoride reacts, you lose X and you produce X, so plus X of the hydrofluoric acid, right, and plus X of the hydroxide, okay? And so here you wind up with 0.100 minus X at equilibrium for the concentration of the fluoride, and you wind up with X for the concentration of both the fluoride and the hydroxide. And of course, the other assumption that we're going to make is the 5% rule, and hope that that works out. And of course, with the 5% rule, we can go and say, this goes away, right? That's our 5% rule. Okay. Once you've done that, now you can go and start the calculation. I think I need more space. So let's add a slide here. So let's add in, uh-oh, what's happening? There we go. Yay, technology. So let's add in a blank slide, maybe 2 of them, and continue there. So here we left off, we filled in our icebox. Now we can do our calculation. Our calculation should show that Kb will equal the concentration of HF times the concentration of hydroxide divided by the concentration of fluoride, right? And so that will equal X squared over 0.100, which equals 1.389, where there's our significant figure, times 10 to the minus 11 power. And so we can do our calculation. We can find that X, just by doing a little bit of math, will equal the square root of 1.389 times 10 to the minus 10, right? I get that because I'm multiplying each side by the 0.1 here. And it comes out to give you a value of 1.179 times 10 to the minus 5 power. And that we know is our concentration of hydroxide, right? So that's going to have units of molarity, okay?
What's the negative 12th if you're multiplying by 0.1?
No. Oh, you know what? You're right. Yep. Math error. Oh, man. Stupid technology. Okay. Yeah, you're absolutely right. So here, let's do this. Back up into that. Eraser. Come on. The day for technology right now, isn't it? Oop. That's not going to work. Yeah, thank you, Nora. There we go. That should be a 12. Because math does work. That'd be times 10 to the 12th, which would mean this would be times 10 to the 6th power minus 6 power there. There we go. Yeah, that's better. Okay, thank you. So then we can just basically take that, we can check our assumptions, okay? And so for this one, notice this is a value that is bigger than 10 to the, it's bigger than 10 to the 6 by a tiny, teeny bit. And so if we're doing our checking of the assumptions here, right, if we check the concentration of hydroxide with, from the autoionization of water, hopefully this will work where it's so much smaller than the concentration of hydroxide from fluoride, right? So we check that assumption by saying, and taking our concentration of, so 1 times 10 to the minus 7 molar, right, which is from the autoionization of water, that's our hydroxide ion concentration, divided by 1.179 times 10 to the minus 6th power times 100%, okay? And you actually wind up with 8.5% here, okay? So that does not check out. So we're gonna have to go back and do our recalculation, okay? But what we also wanna look at here is if we check out the 5% rule as well right now, generally if the 5% rule works, it's only gonna be, it's gonna be a small difference in the next one. So if the 5% rule checks out here, it'll probably hold for the other one. We won't have to check it later. So for that, we say 1.179 times 10 to the minus 6 divided by our original concentration, 0.100 times 100%. So that right there will give us 0.0012%. So that one does check out. But what that means for us is because that 8.5%, right, that's greater than 5%. So we're going to go and make a new icebox and redo our calculation. And so now we've got our fluoride ice. I can't wait to get that stylus. So the fluoride will react with the water. To produce HF plus hydroxide. But now, when we go in here, yeah, we have that 0.100 minus X, and we can still use the 0.100 minus X and get rid of that. That 5% rule is going to hold. But when we have our hydroxide ion concentration now, we have to input 1 times 10 to the minus 7 power there, and then X and X, so plus X and plus X. So you wind up with X and 1 times 10 to the minus 7 plus X. And so now you can go and plug that into your KB equation. So you get 1.389 times 10 to the minus 11 will equal X times 1 times 10 to the minus 7 plus X divided by 0.100. Okay, and so here you've got 1.389, again, that's where our significant figure is with 2, times 10 to the minus 12 is equal to X squared plus 1 times 10 to the minus 7 X, right? And so you can get the quadratic equation from this. So you get 0 equals X squared plus 1 times 10 to the minus 7 X minus 1.389 times 10 to the minus 12, okay? And so here, see if I can draw this in here. So you get negative 10 to the minus 7 plus or minus the square root of 10 to the minus 7 squared minus 4 times 1 times negative 1.389 times 10. Sorry, my writing is getting small up there. If I can make it clearer. Come on, stylus. Here, let's try this. So negative 1.389 9 times 10 to the minus 12. Okay, I know it's hard to read, I apologize. That all divided by 2 times 1, right? And so if you give me a second, I'm gonna plug this all in. 1. So you wind up with negative 10 to the minus 7 plus or minus the square root of, that should be, nope, that's not, come on. Sorry, guys. There we go. Should be square root of 5. Come on. So 5.52 times 10 to the, let's see, you have minus, something's off on there. Sorry guys, my calculation's off. Anybody have that answer right there? My calculation is off at the moment.
I think it's 5.53 times 10 to the minus 12.
Okay, thank you. 5.53 times 10 to the minus 12. I was getting something unusually off on that. All right, there we go. So that over 2. And so you have 2 answers here that you can get, right? You can get, so basically on this one, your square root, so -1. So you want the one that adds here, obviously. So negative 10 to the minus 7 minus the square root. All right, so you should wind up with here. There we go. 2.35 times 10 to the minus 6 over 2. So your concentration of hydroxide should equal 1.175 times, or 176 times 10 to the minus 6 power, or 1.2 times 10 to the minus 6, okay? And then you can take that value and we're gonna insert a new slide. There we go, okay. And you take that value and you insert, so with this new slide, you plug that in, so okay, so POH will equal negative log of 1.2 times 10 to the minus 6th power, right? And you should.
Wait, don't we have to add the 1.0 times the -7
Hold on.
plus x?
Sorry, I'm a little out of sorts with the technology at the moment. It's really so I apologize to you. This is one of those steps that Okay, where are we at?
Because otherwise it would be the same as what we got before.
Yeah, you're right. Yeah, we have to add the 1 times 10 to the minus 7 from the concentration of hydroxide. See, this is what happens when I get flustered on this stuff. And this is, yeah, I apologize. Crap. Where we at? There we go. This is what I want to get to. Oy. That kind of a day. Yeah, so you're right. We take this right here, the equilibrium concentration there. That's our X, right? So this should be X equals that, not the hydroxide, right? Thank you for keeping me honest, Nora. One of those kinds of days. All right. So here, concentration of hydroxide should equal 1 times 10 to the minus 7 plus 1.179, go back real quick, make sure I've got it, sorry, yeah, 1.176 times 10 to the minus 6 power, so you've got 1.276 times 10 to the minus 6 power, and so now you take the POH is equal to negative log of 1.276 times 10 to the minus 6. Okay. And you get a POH of 5.89, right? And this value should have sig figs there, which means this value should have sig figs there. And so you can say pH equals 14 minus 5.89, which is going to equal 8.11. You get the pH of that solution. Okay. And so with that, that gives us the concentration or the pH of that, that particular solution, a fluoride solution. All right. So what I want to do here, I'm going to take a quick break. Keep those. Okay. And unshare the screen for a second. I need a second. Well, we're already at 12, so we're just going to end there. So we are going to